So the reason they're teaching you numerical methods within this class, there's a whole class called numerical methods. And it's a great class. Colonel Lindquist often teaches that class. If you haven't taken a class with Colonel Lindquist, that's a great class to take from him. And you'll learn Python as part of it. Just to let you know, how he actually learned Python teaching that class. So I'm going to teach this class in Python for all the code into Python. So it's possible, actually, you might think, well, he's a professor. We have brains that are similar to yours. Mine's older, so it's harder for me to learn. I learned Python as part of the NPH program because in the cloud, you have to use Python. You just switch. I learned R coming here. Everybody was like, we code in R. So if I can learn it, you can learn it. So don't be afraid. Just go in there and try it. And then let me know if you're having any trouble programming. So the thing about these numerical methods is the sad state of it is that most differential equations you write down, you cannot solve by hand. I know, we spend so much time solving them by hand. It's the whole first part of this class. You can do on Mathematica. You can just tell it to desolve it. And in fact, you can tell it to numerically desolve things too. And the most interesting differential equations are the ones that you actually have to get in there and hard code things for. There are differential equations that you can't stick in a Mathematica. It's just not going to do the work. So that you have to come up with a scheme that actually works for it. But we're going to go through one of the most powerful schemes that works for most things. So this is, I'm not sure how to pronounce it. Americans always pronounce this Runge Kutta. The Germans that I was with pronounce this as Runge Kutta. And I'm not going to do the Indian one because I've heard the Indians talk Runge Kutta. So everybody seems to have a different pronunciation for this. There are two last names. Runge is one last name and Kutta is another one. For all intents and purposes, Runge Kutta works for most things. And Euler sucks if you guys haven't seen that already. It seems like it should work just fine, but it sucks. And it's because the derivative, the discrimination of the derivative is unstable. Because if you look at this thing here, you do that, the h is going to be going to 0. So you need really small h's. And when you divide by really small numbers in a computer program doesn't really like it. And so you have to be a little careful with using something like this. So what is Runge Kutta? And I know that Dr. Groves also talked with you guys about the error term in the Taylor series. So Runge Kutta has a local implementation error of order 4. Does that make sense to you guys? This is all new stuff that you're getting. Span the Taylor series, and then you have the 4th order term that's got the error in it. Euler's a 1st order thing, so it has a squared term. Does that sound familiar? Okay, we're gonna go do some of this today. Okay, so let's go through the formula first. I'm going to do a little bit of derivation. Your book has left it out. And then I got to the part where the reason the book left it out was a lot of heavy algebra. I thought, I don't want to do this in class. I'll be sitting there using all the boards all the way across, so I'm not going to do that whole thing. Everybody got this? Maybe what I'll do for your next homework is we'll take these notes, kind of like what I did with the matrix. We'll do the same thing. We'll just have you kind of go through and fill in the gaps so you understand what's going on here. So how does it work? Just like Euler, you're going to chop up your interval into pieces. So you're going to have these chunks of intervals that you're trying to numerically integrate this differential equation over. So is this similar to Euler? And your book actually uses the number of pieces you chopped together as the thing you input into a program. I actually use the step size in my program. So if you think about it, like what's really important, I want my h to be small. So I set my h to be that, and I do my counting later. Right? If you're going to chop up your interval into pieces, then the step size is going to be how small those pieces are. And so what I do is I start with h equal to, I just start there. Usually my go-to h is 0.01. So there are folks that are looking at my code from the weight loss algorithm, and they asked me, can I just set that h to be 1? No, you cannot. And they said it seems to look fine. Like, don't do that. Don't set it to equal to 1. This is why it's supposed to be like close to 0. So it was I had to kind of talk to them about that. But they didn't get this lesson. Then your next upgraded yn plus 1 is a recursion equation that you took MA 103. This is a recursion equation. And they're putting subscripts here. In a computer program, you wouldn't do that. There's 4 parameters that you're going to have to calculate inside your program. And where these come from, these are the weighted slopes. So in Euler, you have the one slope that you're using. Now instead of that, you're using a bunch of weighted slopes over the region that you're integrating over. So these numbers here, I'm going to list them out in a second. So the first one goes for whatever you have at the ordered pair at the left endpoint. So right here, like Euler, you just keep going forward. Right at the Tn interval time point, you know what this Tn and Yn are. So you plug them into your F. What is your F? Where does the F come from? In a computer program, you have to know what to type in, right? So where does this F come from? Yes, so you have y prime equals f of ty. That's where that comes from. So you plug it in there. So in a computer program, the clean way to do this is to make a function below so that you have this function inside and then you're just calling back from that function. If you've done some programming, there he is. I just said they could lean on you for some help with programming. Signed you up. You weren't here, so. Kn2 would be f of Tn plus a half h and yn plus 1/2 h k n1. So what this is like a midpoint estimate. Like inside your interval, you're getting a midpoint estimate of your derivative inside the midpoint of that interval. And then you could also do it below. Let's see what I have here. Yeah, so you're always using the one before. So when you program, this number has to come first. Then you go to assign your next one second from whatever value you get from the first one. And then the third one, you'd have to know this one. So each of these have to come in this order when you're programming this. Can you program in Python?
I usually use Python.
Okay, good. And then the last one is your estimate of the slope at the other end. This is the first slope that you get. So if you have this is the unknown function. You're trying to recreate this function. Here's this Tn. Here's this Tn plus 1. You can estimate the slope here. and think of it as a tangent line. So you can estimate a little, and then you want to go forward on that tangent line up here. That's how you get your second estimate. And then over on this side, you have an estimate of the slope here of this unknown function. So, and then you just average them all. That gives you an estimate of the slope inside that Tn to Tn plus 1. So this is my hand waving kind of explanation of why this works. Okay, so let me label all this. This here is the approximation of slope at Tn, Yn. These two guys down here are approximations of the slope at midpoint. And the last one is this is the approximation of the slope at the endpoint. All right, so I went through a little bit of where this formula comes from. I'm actually going to show you a little bit with Taylor series. Did you guys do Taylor series last time with Dr. Gross? Not sound familiar? Okay. Is this all making sense? What's going on? Life is evil if this thing doesn't work, actually, because then your equations are really hard. Maybe I'll give you an equation where it does something like that. There's these equations that come from, it's called the Blasius equation. It's a third order differential equation, and it's supposed to be for boundary layers. They use it to build planes so that, you know, if you think of a plane that's going through air is a medium that it's going through, and it has the same, like if you've ever seen on a river, there's a layer that comes up on the side of a rock. That's called the boundary layer. And the Blasius equations actually predict that boundary layer. And you want to know those things when you're designing your plane because you don't want to have it pushed down. So those equations are nice. So maybe we'll try that with Runge Kutta sometime. All right. Okay, where does this formula come from? Maybe I'll pause here and I'll show you some programming stuff first, like how to implement it, and then I'll come back to this Taylor series stuff.